Now, the first thing, very easy to do, is instead of having a fixed position, let's randomize this direction. Let's say this distance. Let's say it's going to be fit 0, 1, a random number based on the ID that we're going to be fitting between, let's say, minimum distance should probably be 0.05, maximum 0.2. Let's see if this makes sense. Let me just expand this. Okay, so now we have different distances between these points. Okay, these are different, these are different, these are different. Okay, so they're always going to have a different distance between them. So this is a start. The next thing that would be really cool is if we could kind of make this vector, the vector that we're currently using here. Let's have a look at these vectors again. This yellow vector, what if we could kind of make it rotate around this axis? So as it goes by, as time goes by, as the particles are sliding across the surface, these vectors are also kind of rotating a bit. Okay, that's the next step. So how can we rotate this vector? So to rotate the vector, we first need to calculate how much it's going to be rotating. That should be the start. How much is it going to be rotating? And we want to have a float that controls that. And that float should be dependent on time. So time times something. And let's fit 0, 1. Same thing like here. So let's use this. Let's actually grab the whole thing. Control C, Control V. I do like to keep some space here. And so it's going to be random ID. Let's add some random number, and the values here need to be kind of a bit different. So this establishes the rate at which it's going to be rotating. So let's say something between 2 and 4. Let's see if this gives us enough. Between 2 and 4. So we have a rotation that's going to be applied to that vector. So it's just going to be a matter of us applying the rotation to that vector. The way we do that, or the way we can do that, is let's create a matrix called M, and it's going to be an identity matrix. I'm not sure how familiar you are with matrices. Matrices are pretty handy. And for this type of transformation, alignment, rotation, transforms, and all that, it's definitely something you should have some notion of at least. So I'm creating an identity matrix, and we're going to be rotating it. Let's rotate that matrix. And this may seem weird, but because usually we're kind of writing a line of code that's going to be equal to something, but in this case we're just going to be changing the matrix itself. We don't need to save it. It's already it's going to be just changing the variable m, which is the identity matrix. So it's going to be rotate matrix m by the amount my rotation, and based on the axis normal, ref norm. Okay, so now we have the matrix that has been rotated the amount that we want. And the beauty of this is that now you can multiply the vector that you actually wanted to rotate by this matrix, and you will get the result that you were dreaming of. So let's say that side is going to be equal to times equals m. Okay, and this will give you the rotated. Click, and we have an error because I'm missing some thing there. So we should see the yellow vectors rotate, not just changing direction based on the normal, but also rotating. You can see on some of them it's actually pretty clear. This one, for instance, you can clearly see that it's doing something. It's rotating a bit. Let's exaggerate. Let's go with 5 and 10. Okay, so now they're one thing we can do is actually just go to the pop network and remove the force, stop the force, so that they don't go anywhere. We are updating the position. So this is already the new position. This is not what we want. We just want them where they were. And as you can see, they're born and they have a spinning vector attribute. And now let's update the position. These are no longer relevant because we are actually looking at the final target, and that's what we wanted to do. So we have the position updated. These we don't need. This was all temporary. All we want is essentially to update the position. And now we should see that not only do these particles are all generated based on with different distances between each other. I mean the blue and the orange one, but they're also kind of rotating in relationship to each other. Okay. Of course, we could take this one step further and not just have them rotate, but have them um, kind of go further away from the origin, for instance, at a specific rate. That's something we could also do. But for now, I'm just going to leave it like this. I think it's complex enough, and I'm just hoping it's not too complex already. But yeah, these were just helpers for me to try to illustrate what was happening. But essentially, we're looking for the nearest point on the surface, grabbing its normal, using that normal to create a temporary vector that will allow us to calculate a more tangent to the surface vector, a side vector. And then we are generating a new position that's going to be stuck to the surface based on that vector. In order to make things more interesting, the distance along the side vector that we're projecting is randomized for each particle here. And we're also rotating that vector through time at different rates. Let's say that these rates are a bit too much. So 3.6. I think these were working fine. And yeah, that's pretty much it. Now we have 2 points that we can merge together. So not like this. Let's just add a merge. I'm going to keep that just for illustration purposes. It may be handy to kind of figure it out. So we're merging, and each point will have his corresponding sidekick with the same ID. So now we can add polygons by group based on ID. Okay, so now we have our starting points, our lines, our starting lines for the arches. And these are going to be sliding across the surface. Let me actually put the color here so that we can see the different edges. Okay. I think this illustrates it better. Blue to orange. So in the next lesson, we'll see how we can transform this into an actual arch and animate it properly.